Décollage et décollage, lift-off.
That's one small step for man.
Hello, welcome to the March edition of Final Frontier, the program that keeps you up to date with the worlds of space science and astronomy. On tonight's program, Invading Mars, we meet Dr. Robert Zubrin, whose amazing concept for a humans to Mars mission has been adopted by NASA.
Going to Mars is easier than going to the moon was in 1961 when Kennedy started the program, and we were there 8 years later.
Observing the invisible, Chris Riley meets a physicist who is searching for that elusive dark matter using an underground observatory. Gas giants, binary stars and spectacular gas clouds, they're all up there in the March night sky. We show you where to find them in our virtual planetarium. Keep in touch via our website at www.open2.net and join us on our journey to the final frontier. This is the Challenger Learning Center, where every day groups of adults and children simulate missions to the Red Planet. But we're moving away from the realms of science fiction, and engineers now have real plans on the drawing boards to send humans to Mars. Some want to go to Mars to look for life, others to study the planet's spectacular geology. But when we do go, one thing is certain: it will be the greatest adventure in human history. A journey to Mars is 1,000 times further than a journey to the moon. Yet, space engineers believe that Mars is now within our grasp. And at least one US president has already said that he thinks we should be going.
I believe that before Apollo celebrates the 50th anniversary of its landing on the moon, the American flag should be planted on Mars.
The plan NASA put forward in response involved a huge spaceship constructed in Earth orbit, which had to be big because it needed to carry all the fuel and the supplies for the eventual return journey. The NASA plan was ambitious in scale, but it had one big political drawback: the price tag of $450 billion. It was quietly brushed under the carpet. Enter a NASA outsider, Dr. Robert Zubrin, maths teacher turned space engineer with a talent for fresh thinking. He thought about a Mars mission and what the planet itself had to offer.
I and others at the Martin Aerospace Company, where I was working at that time, looked at that plan, and it just didn't make any sense, because they were sending these huge spaceships to Mars, fully loaded with all the propellants for a round-trip Mars mission, and yet sending rocket propellant to Mars makes about as much sense as sending oil to Saudi Arabia, because Mars's atmosphere is the ideal feedstock for making rocket fuel. So, I mean, after all, why are we going to Mars in the first place? Because it is the planet that has the resources needed to support life and therefore potentially someday civilization. Well, the same resources that make Mars interesting are potentially what can make it attainable.
Zubrin's idea was to send ahead of the human crew a robotic fuel factory with a supply of hydrogen on board. By combining this hydrogen with carbon dioxide from the Martian air, Zubrin realized that you could make methane rocket fuel. So when the first pioneers arrive, they'll be able to explore the surface, safe in the knowledge that their return vehicle is fully fueled and ready to go for the homeward journey. Zubrin's concept, called Mars Direct, has now been adopted as part of the official NASA plan, the Mars Reference Mission.
Because your return ride is waiting for you on the surface of Mars, you don't need to fly to Mars in a gigantic Battlestar Galactica spaceship constructed in some futuristic means on orbit. You just fly to Mars. This one goes with the crew in a habitation module, which is basically a big tuna can with a life support system installed. And that goes and lands on Mars in the general vicinity of the Earth return vehicle. Use that as your house on Mars while you explore Mars for a year and a half. And then when you're done, you get in the Earth return vehicle, you take off, and you fly back to Earth. When it was first proposed in 1990, it was considered a very radical plan. Although I must say that we got a certain faction of support from within NASA more or less immediately. At virtually every NASA center, there was a certain contingent of people that immediately saw that Mars Direct was the way to go. NASA has accepted many of the ideas in the Mars Direct plan, and that's very good because that has reduced their estimates dramatically of what a human Mars mission would cost. But it still remains the case that we have to convince the political class to actually launch such an initiative. Now, that's a question of vision, and it's a question also of convincing them that the public stands behind this, and that's one of the reasons why the Mars Society does a lot of outreach. We have to convey to the political class that the public wants us to continue to be a society of pioneers, that the public understands that we have everything we have today because our predecessors were pioneers. They were willing to go places that no one had ever gone before and build things that had never been built before and attempt things that had never been attempted before. That's why we have everything we have today. And that if we want to give our posterity a promising existence, we have to be willing to carry on that kind of tradition.
At the present time, the human exploration of Mars is simmering away on the back burner as far as NASA is concerned, but they do continue to focus the plan. Scientists are working on inflatable space habitats, oxygen and water recycling, propulsion systems, and even ways of generating artificial gravity for the crew. And, while NASA keeps Mars in its sights, Robert Zubrin is out inspiring interest.
If we had a commitment to send people to Mars, we could certainly be on Mars in 8 years. Now, we don't currently have a commitment, but we continually roll the dice politically in the United States and elsewhere. And this is an idea whose time has come, and as soon as we have political leadership willing to embrace this vision, we'll go in fairly short order. So I believe we could be on Mars by 2010. I think we will, in fact, be on Mars before 2020.
Well, that's a fantastic vision, but what steps are we taking to actually make this a reality? With me to discuss this is Bo Maxwell, who's the president of the UK chapter of the International Mars Society. Bo, what is the UK Mars Society involved with then?
Within the UK, we're very heavily involved in promoting the Mars Direct mission, which we've just had a look at, and more particularly taking direct steps towards humans to Mars through the Mars Analog Research Station project.
Now, what is the Mars Analog Research Station?
This is a project to establish 4 bases around the world. 1 in Canada, 1 America, 1 in Iceland run by the Europeans, led by the United Kingdom, and 1 in Australia, where we're going to be carrying out some very real science in preparation for sending humans to Mars. Basically, it's a simulated Mars base, what you might consider to be a baked bean tin on Mars, in which 6 people can live and work for long periods of time.
Now, what exactly is the function of these things?
It's to enable us to research the ways in which people will live and work and carry out scientific experiments when they're actually on Mars.
Now, presumably these locations are chosen because they're analogous in some way to the Martian surface.
That's absolutely right. They are very, very similar, as close as we can get in Earth terms to Mars. They have terrain that's very similar to Mars. They have geomorphology that's very, very similar to Mars. And potentially we may be able to find some what we call extremophile life there that's similar to the kinds of life we believe may exist subsurface on Mars.
Now, what direct UK involvement is there with these projects?
Within the UK, we're very heavily involved with the European Mars Analog Research Station, which comes on stream in 2003. We're directly responsible for fundraising for this project. We're also very heavily involved in the design of the unit itself, which will be a habitat, very similar to the one we saw in the film, supporting up to 6 astronauts. And we're putting together a lot of the background supporting technology, radio systems, simulated Mars EVA suits and life support systems.
But at the end of the day, these people are only on the Earth and not actually on Mars. Doesn't that change the way their psychology is going to affect the way they work and function?
It will to a degree, but again, by choosing sites that look very remarkably like Mars, and having been to one of these units myself and experienced it for myself, you very, very quickly get into a mindset where you do believe you're on Mars. And we carry out work in such a way that enhances that by making them wear spacesuits when they go outside of the vehicle, etc., to give them a real feel that they are living and working on Mars.
So this is real practical research that will help humans get to Mars?
Very much so. Very much so.
Well, thanks very much.
Thank you.
Welcome to Space Now, the National Space Centre's news and information exchange service. So what's up in the worlds of space science and astronomy this month? Well, it was a tense moment for solar scientists as they awaited the launch of the HESI satellite. The high-energy solar spectroscopic imager is designed to study solar flares. Watching the live NASA webcast were some rather nervous British physicists who were relying on HESI for their research into the sun's behaviour. The spacecraft was being dropped from the belly of an aircraft at 39,000 feet to be propelled into space on a Pegasus rocket.
3, 2, 1. Pegasus is away. Here we see it.
Bus is strong.
Been 18 months of delays. It's been shaken to pieces at 20G instead of 2G. It's been caught in floods and rescued by the US Army. So now it's actually in orbit, you know, can breathe a sigh of relief.
I'm going to be looking at the solar flares that we get around solar maximum. Basically, we'll be looking at the high energy processes within solar flares themselves and how the solar flow is triggered and how the emissions produced. So it should be exciting.
Well, that should keep those guys busy for a few months at least. So Vicky, what else is up?
Well, scientists have found 5 new Martian meteorites, some of them in the Antarctica and some in the deserts of Oman and the Sahara. It brings the total of known Martian meteorites to just 24, and we're hoping it'll give us lots of clues about whether there was once oceans on Mars and whether there was ever life.
Great, thanks very much. Adi, I hear you've got some news about the International Space Station.
Yeah, there's a group of astronomers in the States that may be getting the opportunity to mount an optical telescope on the ISS. It's going to be controlled by an observatory in Tennessee, but it'll be also linked to the internet, so it's going to give other amateur astronomers the chance to use a telescope in space.
Great, thanks very much. And of course you can find out more information about that and other stories by going to the Final Frontier website and clicking on the Space Now link. Still to come on Final Frontier. It should be the most common stuff in the universe, so why can't we find any? We follow the search for the holy grail of cosmology, the elusive dark matter.
Hello and welcome to our virtual planetarium where the skies are never cloudy. It's 10 p.m. on a chilly March night, so let's take a look at what we can see. Jupiter is still one of the brightest objects high in the southwestern skies, although since last month we've drifted another 26 million miles apart and it is getting dimmer, but it's still well worth a look. Now the stars around Jupiter at first glance might appear to be very similar, all just little points of light, but in fact, with a good pair of binoculars, you'll see that they are all different and individual in their own rights. Many of them are different colours relating to their temperatures, and many of them have got companion stars as well. If you follow Jupiter across to the left, to the southeastern skies, you'll come across a constellation called Leo, and it's a very distinctive hook of stars, of 6 stars, like a reverse question mark in the sky. Now, just below the base of the hook, you'll see Leo's brightest star, a star called Regulus. It's a big blue star, and it's blue because it's a lot hotter than our sun. It's 77 light years from Earth, but if you get a pair of binoculars and have a good look at it, you'll see that there's a very faint companion star to it as well. Just above Regulus, you'll see another of Leo's colourful stars, Gamma Leonis, and in fact, it's a pair of giant orange stars that take 6 centuries to orbit each other. All those objects are in the southern skies, but if you turn 180 degrees around and have a look high up in the northern sky, you'll see the very distinctive markings, the outline of the plough. Now its bowl is tipped up slightly and pointing downwards, and if you follow the 2 top bowl stars down, you come to Polaris, the pole star. Now, if you go back to the plough and follow the handle of the plough down, you'll get to another giant orange star called Arcturus. It's in a constellation called Bootes. Arcturus is an orange colour because it's getting old and it's expanding and it's cooling down, but it's still bright. It's 100 times more luminous than the sun. It's 37 light years from Earth. And if you look closely at it, again with binoculars, you'll see that there's another yellow star orbiting the big orange one. It takes 150 years for them to go round each other. So as you can see, there's a whole variety of stars out there. They're not just the tiny pinpoints of light that they appear with the naked eye. Through binoculars, you can see that there are lots of different colours and different star systems. If you want to find out more about these and other worlds, then take a look at our website. And next time there's a clear night, get out and take a look.
The European Astrofest here at Kensington Town Hall is the biggest gathering of amateur astronomers anywhere in Europe. It's the place to come to find out all the latest gadgets and gizmos and catch up with what everyone's up to. 4,000 people attended the two-day event that was organised by Astronomy Now magazine. Why are you here at Astrofest?
I'm here looking at all the different sorts of equipment, because I'm obviously looking to purchase a telescope. And this is the best place to come, is to see the number of manufacturers here.
It's the only gathering I've seen like this in the UK. It's certainly worth a couple of days of my time every year.
So Robin, how are visitor figures at the Royal Observatory going now that you're not charging any?
Oh, well, we've seen a really big increase. Now it's free entry. It's fantastic, yeah. So I don't know what's going to happen in the summer. It's going to be absolutely full.
Great.
Yeah.
Oh, it's been really encouraging today. We've had lots of young people coming up asking questions about careers in space science and technology, astrophysics. So been giving out information about different events and projects that are going on both in the UK and abroad. Yeah.
So Nick, if I've got 100, maybe 200 pounds to spend, what can I expect to buy for my money?
You can expect to buy something like one of these two telescopes. We've got a refracting telescope here and reflecting telescope here. These are entry-level telescopes. They'll show you basic objects in the sky, things like open clusters, good views of the moon and the planets. There's no motor system on them at all. They're basically used for just general observing.
Right. Now, assume I've got a few £100 more, £400–500. These sorts of telescopes are now obviously the sort of machinery I might expect to buy for my money?
That's right, yeah. Once you've got a slightly higher budget to work with, you can start coming over to these telescopes. These are what we call go-to telescopes, in that you can press the coordinates within the database. The telescope will slew onto objects in the sky. They make observing a lot easier.
Great. So they basically have a database of objects in there.
It's quite an extensive,
they know the sky.
Yeah, that's a very extensive database. You can just star hop from one object to the other across the sky, and they make observing a very sort of pleasurable experience.
Now, assume my budget is in the several thousands of pounds. What can I expect to buy then?
Well, then you can expect to buy something like this telescope here. This is a 10-inch Schmidt Cassegrain, actually just come into the country within the last few days. This is utilising new GPS, Global Positioning System technology. And there's a whole host of improvements on this telescope to make it an ideal telescope for CCD work, for photography and for general visual use. And these kind of telescopes will probably prove very popular with universities and sort of general educational establishments.
Why would anyone want GPS on a telescope?
Well, GPS allows the telescope to know exactly where it is on the Earth's surface, and in that sense the telescope will actually set itself up, it will level itself, slew onto the first alignment star, so really all the user does is switch the telescope on and come back in 5 minutes and the telescope's completely set up and ready to go.
Sounds like it's cheating to me.
Light is precious to astronomers. By looking at parts of the night sky that shine, we've been able to build up a pretty good picture of what's out there and how it works. But what about the stuff that doesn't shine? Well, from up here on the London Eye, I can see the city lights down below, but I know that there's buildings amongst those lights. There's a dark river as well somewhere, an even darker park somewhere behind us, and there's millions of rather unshiny people somewhere down there too. And the only reason I know that they're there is because I've seen London in the daylight. It's a picture that's very much like the universe. The laws of physics tell us that the force of gravity holds the stars in the galaxies together. But gravity requires mass, and the stars alone don't account for enough mass to produce such a force. There must be something else out there, maybe in a cloud or halo surrounding the galaxy. And there must be lots of it too, because if the calculations are correct, the shiny bits only make up about 5% of the universe. This missing ingredient is called dark matter, and the race to find out what dark matter really is has been one of the most fiercely contested in the history of astronomy.
Most things are dark. I mean, stars shine, hot gas shines, we are visible, but only because of reflected light. So most things in the universe are dark, and I've always taken the view that there will be far more forms of dark mass than there is visible mass.
Being shiny is hard. Lots of complicated things have to happen. Stars shine because they have nuclear reactors in the center, and for nature to build a nuclear reactor is not that easy.
If dark matter doesn't exist, it means the laws of physics are wrong, and everything we think we know about the universe would be turned on its head. The stakes in this quest are extremely high, because whoever actually discovers what dark matter is will probably get a Nobel Prize and scientific immortality. The battle for the prize has been fought out on two fronts for the last 20 years. On one side, the particle physics camp, who believe the answer lies in the fundamental laws of physics. And on the other, astrophysicists, who see observation as the key.
Well, in principle, the dark matter could have turned out to be anything. It could have been dead planets, failed stars, black holes, old socks, anything was possible. But in the 1980s, most possibilities were eliminated, and there were really two possibilities that survived.
The first type of candidate was the so-called baryonic dark matter candidate. Now, baryons, they're the ordinary, that's the ordinary material made of atoms, like you and me. And the baryonic candidates are things like the remnants of stars, black holes, or very low-mass stars, so-called brown dwarfs, which were never really large enough to produce a lot of light.
These objects would appear in the halo of our galaxy, and they were baptized with the name of massive astrophysical compact halo objects, or MACHOs for short.
They were naturally favored by the astrophysicists because everybody wants to explain dark matter in terms of what they're used to. So the astrophysicists would like the dark matter to be explained in terms of MACHOs. On the other hand, there were the so-called non-baryonic dark candidates, and these were elementary particles from the early stages of the Big Bang. They were sometimes called WIMPs, weakly interacting massive particles. And the particle physicists who got involved in cosmology at this time, they were naturally very keen that the dark matter should be in the form of WIMPs.
I am a believer that the universe is full of WIMPs, and that it is the WIMPs which are actually turn out to produce the strong men in the universe are the WIMPs, because it is these WIMPs that keep the galaxy clusters in place, it's the WIMPs that keep galaxies together.
So on one hand we have the MACHOs, great heavy lumps of ordinary matter like free-floating planets, failed stars and black holes. And on the other hand, the WIMPs, tiny exotic elementary particles that have been hypothesized but never seen. The debate raged in the 1980s and 90s, and at first it seemed that the MACHOs were going to be the most likely contender.
We would all go to the same conferences, and I favoured, because I was an astrophysicist, I spent most of my time working on the MACHO candidates, first on the black hole picture and secondly on the brown dwarf picture. There was a time in around about 93 when people got positive evidence apparently for MACHOs. This came from the so-called microlensing experiments. They would look at stars in the Large Magellanic Cloud, and they would find that the luminosity would vary because a MACHO had gone across the line of sight, and the lensing effect had changed that luminosity variation. And that was very exciting because at first it looked as though that was positive evidence that the halo dark matter was in fact in the form of MACHOs.
A good feeling as an astrophysicist.
It was an exciting time.
The news was splashed all over the newspapers. It appeared as though the dark matter had been found. And I've worked all my life on WIMPs, and I have reasons to believe that the dark matter is made of WIMPs. And clearly many of my colleagues and I, at one level, we were somewhat downcast because clearly the initiative had passed on to the MACHO camp. At another level, we were pleased because we recognized that the dark matter problem is such an important problem, and even if the solution was not our solution, at least the problem was being solved. But I have to admit that I was skeptical.
This skepticism was proved to be correct. Despite a huge international effort to find more MACHOs, far too few were ever found to confirm the theory. And the path was left clear for the particle physicists to prove that it was WIMPs that held the universe together.
The current view is that the microlensing observations towards the Large Magellanic Cloud won't allow you to have more than 20% of our own halo in the form of MACHOs. And so that means that even the majority of the dark matter in our own halo must be made of WIMPs. However, 20% is still a lot.
I think the pendulum has swung, the MACHOs have had their day, and now it is the turn of the WIMPs to see whether they can rule the cosmos.
In computer simulations, virtual WIMPs do a very good job of holding the universe together, but we still haven't found a real WIMP. The trouble is, from Earth, they're incredibly hard to spot amongst all the background noise, especially from cosmic rays. So you need to go to a place where WIMPs can penetrate, but cosmic rays can't, like here at the Bolby Salt Mine in North Yorkshire. Every 100 meters we go down, there's 10 times less radiation noise than we get at the surface, until here, over a kilometer underground, it's 1,000,000 times quieter.
So we're 1,100 metres down here, so that means that we...
This is the home to the experimental headquarters of the UK Dark Matter Collaboration. It's one of a dozen experiments worldwide looking for WIMPs. So Nigel, this is it?
Yep, this is our latest detector, which uses liquid xenon. And as you can see, we're surrounded by a pile of high-purity lead to shield it from the low levels of radioactivity in the wall around us.
I mean, it's really substantial shielding that you've got here, even though we're over a kilometre underground. And why do you need even more?
Yeah, there's about 60 tons of lead here, and although we've got away from the cosmic radiation by coming a kilometre underground, there's still very low levels of radioactivity in the rock salt around us.
So do you think you're barking up the right tree with this kind of detector then?
Absolutely. The current theories from particle physics, the latest theories that people are looking at the moment, predict particles that would have the characteristics that would fit exactly the sort of particle that we're looking for to solve the dark matter problem. And that's where the synergy is coming in between particle physics and cosmology.
Do you think you'll ever find any in your lifetime?
Oh, absolutely. This is what gets me out of bed in the morning. The idea that we're currently developing is how you improve the sensitivity of your detectors. And the basic principles we're looking at is using better discrimination between the particle we're looking for and those we're trying to reject. And we have a program of work mapped out that will allow us to explore the whole sensitivity region that we need to look for the particles that we're being told to look for by the theorists. So yes, I think we're in a very good position that over the next 10 years we will be able to identify this stuff.
I think these dark matter experiments are a little bit the venture capital of science, that any one experiment is unlikely perhaps to be successful, but the one that hits the jackpot really made it big. And so in my opinion, it's worth, any reasonable scientific program must have an investment in this sort of high return science where it costs you some money, but if you win, you can then put your feet up for the rest of your life because you've done it. You will have solved one of the major problems in science.
And so I always take the Sherlock Holmes view, which is that once you've eliminated the impossible, whatever remains, however improbable, must be the truth. And I think it's important, therefore, to be looking for all of these different forms of dark matter candidates. And if you end up excluding them, fine, that's a valuable advance. One by one, you can exclude the various macho and WIMP candidates, and then what is left is the truth. Because we cannot yet claim we've got definitive evidence for the WIMPs. We haven't detected them. So the best thing you can do is to show that everything else doesn't work.
There is a race on at the moment, a very heated race, and I think that when people are working under this kind of pressure to make the most important scientific discovery in the history of physics, you have to expect that they will crack it soon. And I would say that within the next 5 years, in a pessimistic way, perhaps the next 2 years, we will see finally in the laboratory, that is in these underground experiments, we will see the WIMP that struck the instrument. And I would say on a timescale of 2 years, 2 to 5 years, this race should come to an end. If not before, it could happen tomorrow.
And that's it for the March edition of Final Frontier. Next month, if you haven't got a telescope, don't despair. You'll soon just be a mouse click away from the telescopic wonders of the universe. We'll be launching the Final Frontier Virtual Telescope. Do join us then.